everyone who is missing it.
Okay, should be started.
Okay, Evangelos, now it's all yours. You can get started.
All right. So can you hear me? Can you hear me?
Yes, we can hear you.
Okay. And can you see my slides?
Yes.
Okay. All right. So we have a delay in the feedback, but it's okay. So yeah, it's my pleasure to present today. The presentation will have 3 parts, and it's in the first part we are going to present our most recent work on robust model predictive control architectures, and there we will see how we can use differentiable optimization for tuning these model predictive control architectures. Within these architectures, we use this concept of barrier states for safety purposes. In the second part of the presentation, we will kind of go a little bit deeper into barrier states and how they can incorporate it into trajectory optimization and optimal control. And what we will kind of see is that we will see what are the limitations of barrier states and how we can kind of motivate the next steps to deal with these limitations. And then in the last part of the presentation, we will talk about algorithms that we use. We have developed recently for training neural networks, especially neural networks that are used for perceptual tasks, to robustify them against adversaries. This is something that involves applications of optimal control and dynamical systems theory to the way how neural networks are trained. And then it's not here on the outline, but there's a last part in the presentation where I'm going to be talking about where we go next, given the work that we have done in this last year, what are our next steps, and how we can kind of integrate the different aspects that we have, namely the robust model predictive control aspect, differentiable optimization, safety with barrier states, and perception. So the first part of the presentation is going to be given by Alex Osen, who is a former NASA employee, and now he's here. He's a PhD student in the ML PhD program at Georgia Tech. The second part of the presentation will be given by Hassan, who is a senior student, PhD student in my lab. He's graduating in 4 or 5 months from now. And then the last part of the talk is going to be given by me. This is work by Panos Theodoropoulos. I will be talking about this last part together with the conclusions and next steps. So let me then give the laptop to Alex, and Alex can go from there.
Sure, sounds good. So yeah, I'm going to start by talking about the differentiable optimization for robust MPC. And so the main motivation here is we're in the process of designing a controller for autonomous systems, such as like a self-driving car. And so we really necessitate that our controller is robust to uncertainty in our dynamics, disturbances in the environment, and that might come in the form of, like, say, gusts or turbulence that affect our vehicle. And we also want our controller to be robust to dynamic obstacles. And so for an autonomous car, this could take the form of pedestrians or other vehicles in the world that we're interacting with. And so our main controller desiderata or criteria is that it needs to be safe, it has to be optimal, and kind of importantly for these autonomous systems is that the control has to be efficient. And so the field of robust control has kind of studied these problems. So it gives you ways to design controllers that are both safe and optimal, but not all of these algorithms are very efficient. But there is one class of these algorithms that has proven to be efficient, and they're known as two-based model predictive control algorithms. So they are computationally efficient by taking advantage of model predictive control, and they're able to maintain safety and optimality while doing so. And so kind of a brief overview of these two-based MPC approaches is that let's consider like we're trying to control this autonomous car here. I don't think I have a pointer here, but we're trying to control this car and we want it to remain in the black bounds. So that could correspond to like lanes or say a racetrack that we're trying to drive along. And so two-based MPC approaches divide the problem into two layers. So the first layer is a nominal controller, and it basically generates a nominal trajectory that you want to follow. And then the second layer is a feedback controller that augments your nominal system, and it basically guarantees that the true state remains safe in the presence of uncertainty. And kind of something I want to highlight real quick is that actually computing the tube is kind of intractable, especially for nonlinear systems. And so really it exists for theoretical bounds. So what these two-based approaches can say is that given some knowledge of the uncertainty, we can guarantee the true state remains in this safe tube. And so these approaches have some downsides actually. So as I said, there's no free lunch. So you actually have to know the uncertainty a priori. These methodologies have difficulty actually responding to the environment, especially if there's very large disturbances. And then they're also notoriously difficult to tune. And that is kind of a function of, because you've essentially added another controller to your control problem. So now the parameters of your controller have a very like nonlinear effect on the resultant solution. And so kind of to address these three disadvantages of these two-based approaches, we propose to add on a differentiable optimization layer. And so we're titling our algorithm differentiable two-based MPC. And in summary, it enables this differentiable two-based MPC enables one to tune your controller parameters online and in real time, but in a principled manner. So principled here meaning optimal. It allows the controller itself to respond to the environment. And a key aspect is we don't have to make any assumptions on the disturbances a priori. So we're actually able to respond to the disturbances that we're experiencing. And then to enforce safety, we're using, as Evangelos mentioned earlier, we're using discrete barrier states, which Hassan will talk about a little bit later in more detail. And then I'm going to quickly go through some of the theory. So essentially, differentiable optimization is basically how you take gradients through an argument operator. So when you have an optimization problem, you have some solver. It gives you a solution, and that solution is essentially approximating an argument operator. And I take gradients through that. And the optimal control problem. And so here we have an optimal control problem. It's a function of the parameters, and we're going to ask the question, okay, how can we choose these parameters optimally? To do so, we'll divide this upper level loss function that kind of encodes like what optimality means. function actually acts on that solution to the lower level control problem. So now we have this kind of high level optimization. At the high level, we're minimizing this loss function with respect to the parameters. And those parameters actually determine the solution to the lower level control problem. And then the next question you could ask is, okay, well, how do we actually compute these gradients with respect to the parameters efficiently? And to do so, we'll use differentiable optimization. And so if we look at the, if we look at the chain rule for this gradient term we're trying to compute, it ends up decomposing into a Jacobian term. So dz star term on the right is pretty easy to compute. Usually it has an analytic or closed form expression, but the Jacobian term is, and so to actually compute that derivative, we'll use the implicit. It's a lot of words, but basically for computing that. And kind of the key aspect is and it's going to turn out that the choice of f for the optimal control problem is going to be the gradient of your Lagrangian. And so the Lagrangian comes from constraint optimization. It's basically like the cost you're trying to minimize augmented with your constraints times some Lagrange multipliers. In this case, the constraints we're looking at are the dynamics. And yeah, when you actually find a solution to your control problem, you're actually finding a point where this Lagrangian is equal to 0. And so that's why of the Lagrangian knowing this now, we have a method for computing this Jacobian term. And this is kind of what we go through in our paper. This like theoretical derivation, we're actually able to generalize a bunch of prior works in the field. And kind of the big picture summary is that approximation to the problem is going. And then the kind of key insight to solving this problem efficiently is that solving the system here on the right is going to be equivalent to actually performing one iteration of DDP. And so DDP is differentiable dynamic programming. It's essentially a second order optimal control algorithm. And it's very efficient computationally. And so kind of in summary, we're able to take these parameter gradients for free. And for free, meaning that it really only requires one extra iteration of our control algorithm, in this case, DDP. And we're actually able to reuse the matrix factorization from the final iteration of our DDP solver. And so that enables the computation to be very efficient. And so we can kind of contrast this with, say, automatic differentiation. So in that, we would have to actually unroll all of the operations of our DDP solver. But in this case, and so that would incur a cost of roughly OK, where K is the number of solver iterations you needed to converge to a solution. But in this case, using the differentiable optimization, you actually get an algorithm that's O of 1, so constant time with respect to the number of solver iterations. And then some examples of these learnable parameters. So that theta vector, these could be your cost function weights in your nominal controller. We're going to see an example where it kind of has this interpretation of your sensitivity to obstacles, and that's going to determine the tube size in this tube-based MPC approach. And they could also correspond to, say, unknown coefficients in your physics-based dynamics model or the parameters of a neural network, things like that. And so to return to the two-base MPC problem, I've kind of written it in the parameterization that we're going to show in the results. So at the high level here, there's this nominal control problem that's going to generate your nominal trajectory that you want to follow. And that's essentially a simple optimal control problem. So we have a cost function we're trying to minimize. That's in the Arkman there. And then we have constraints, so subject to our dynamics. And then we have a safety constraint, which is the last line in that box. And then the safe set we're trying to remain in, so Z, which is a function of theta bar, that's going to be where that sensitivity to obstacles is incorporated. So that's why Z is parameterized by theta bar. And then we're going to augment that system with this ancillary control problem. And this is basically the feedback controller. So it's kind of trying to keep us close to the X bar and the U bar that we get from the nominal control problem. And then that control problem itself is a function of its own parameters, which we call theta. And then we're going to use differentiable optimization to optimize for both theta bar and theta. And yeah. And so I think I'll just quickly skip this slide because in the interest of time. And so at a high level, this is kind of where our work falls in line with the other works on the computation side. So what we've shown here is the top plot is the error essentially of the approaches. Essentially a full second order approximation that I kind of talked about. And you can see that our method is essentially like an order of magnitude faster than differentiation. And kind of like a key piece here is this Amos et al. Differentiable MPC, and it's very well-known work in this field. But one of the issues with their work very fast, it actually results in incorrect gradients for the problem that you're trying to solve. So yeah, our work is essentially like an improvement over theirs in that regard. And then some quick experimental compared to a standard nonlinear two-based MPC approach. And so success here is defined as reaching a target state that we want to reach, and then something that something that I wanted to highlight was that the differences are very large actually for these systems. So it's roughly like on the order of half the maximum control that we're able to apply to the system. And then for the robot arm, it's actually roughly 5 times the control magnitude. And it actually is able to perform very well. And I'll talk about them in detail now. So the first example is this Dubin's vehicle example. So we're trying to reach, starting from the origin, we're trying to reach this green are obstacles we want to avoid. And then the orange trajectories are trajectories controlled under the baseline nonlinear two-based MPC. And then the blue trajectories are our proposed differentiable two-based MPC algorithm. And you'll notice that our proposed is safer and it completes the task with higher probability. That occurs between the obstacles where the tube size and shape actually kind of compresses to be more safe when you get close to obstacles. And yeah, in the next example is a quad rotor example. So again, the disturbances are fairly large, and you can see here there's like a black trajectory we're trying to follow that goes between the obstacles, and it's fairly aggressive. And so when you apply the nonlinear tube-based MPC approach, you end up getting diverging trajectories. But if you use our approach, the DT MPC, we're actually able to respond to the environment effectively and reach the target with higher success. And then I think finally we have like a robot arm example. I'm not sure if the video is going to play, but at a high level, basically the left video would have showed the nonlinear tube MPC. And then on the right, our algorithm is essentially able to kind of squeeze the arm between the space between the cylindrical obstacles and reach the target. Yeah, that's pretty much all I have on this aspect.
Thank you very much, Alex.
Yeah.
We go now to the second part of the presentation where Hassan is going to be talking about barrier states and how they in the previous presentation states and the way how they were tuned was through this approach of differential. So yeah, let's go now with Hassan. Hassan, the audience is yours.
Yeah, thank you, Evangelos. I'll talk about the idea of barrier states here, and then some implementations of barrier states within optimization. I'll be introducing multiple concepts. So basically, this is a general setup of the safety critical problem, where basically some nonlinear system that is subject to those safety constraints. Safe set, controlled, and variant. So basically, once we start in this safe set, we stay in this set. And so the goal here is to design a feedback policy that achieves any other performance objectives while ensuring safety or ensuring controlled invariance of this safe set. And so the idea of barrier states stems from barrier functions in optimization. So as you may know, for classical barrier functions, basically are functions that are smooth and the feasible set, and that basically blows up as we approach the infeasible regions or unsafe regions in our case. And so the idea here is to derive the barrier functions evolution over time, and then augment that or those kind of dynamics to our system, and basically now deal with this system that we call the safety embedded system. So now, instead of dealing with the original system with its constraints, we deal with this augmented system here with the that has the states of the system as well as the states of the barrier. And so, for example, here to illustrate the idea, for example, let's say safe regulation problem here, we define this barrier state and we augment it to the system. And so basically the idea then, or the promise is that if we stabilize the new system, then that means we have stabilized the original system. Unstable, that's subject to some that space while, for example, we have some performance objective, like, closed loop pulls at some, some point, some values like mine. We construct the linear system, and then we simply use pull placement, which is a very simple control method to derive some controller that's the function now, as you can see, of the barrier. So this, although this we have used a linear control method, we have really achieved a nonlinear controller for this inherently nonlinear control problem. And so just to see the results of this controller on the system, here, as we can see, and the left is a phase portrait of the closed loop system under that controller. And as we can see that the system or the behavior of the closed loop system is really nonlinear, where the vector fields approach the obstacle but then start to turn away from the obstacles, and as can be seen also from some trajectories here. So now, this is the idea of barrier sets is also really helpful in the context of optimal control, for example, because as we just saw that we were able, for example, to use simply pull placement. Now, the same, legacy control methods and control can be used directly. And so, for example, if we have this optimal control problem that has subject to the dynamic, introducing the barrier state methods like solving the HJB equation, and then we can also derive kind of a closed form for the safety embedded optimal controller. Applying how the embedded state, or the barrier state basically plays a role. And as we can see here, the feedback, as we saw before, the feedback of the barrier set, which also kind of ensures safety. And so the forward and optimal control is also done over the barrier. The algorithm is aware of kind of the safety of the system. And so here are just some implementation on different systems. We can see that we're able to really kind of navigate safely in some cluttered environment for some Dubin's vehicle systems, cart pool, and a quad rotor. So also we have compared, here's just a comparison against other barrier-based methods like CPFs, control barrier functions, and penalty methods used in optimal control. And we're able to really kind of show a much higher success rate in terms of safety and completing the task. Here we have also kind of here switching arriving basically to that's using also the same algorithm. How about like the well-known methods like augmented Lagrangian methods, and how are they kind of related, or are they different? Cons, and so some for they provide safety guarantees and convergence. The system with respect to the safety relatively easy to pose some limited exploration, because since the idea of barrier set depends on barrier function, then only and so and a problem that would limit kind of exploration also as local minima around the obstacle. So when it couldn't find a local solution, stop and kind of get stuck in a. Now, on the other hand, we have the augmented Lagrangian, for example, method that basically relies on treating the constraints kind of as soft constraints in the cost function. And so to kind of to happen. And so this is good because sometimes we really need to start with maybe some infeasible or unsafe solutions and then try to converge to the safe solutions. However, for AL, there is no kind of converge to a safe solution. On a safe solution, and it requires a substantial amount of tuning. Our optimal control problem and trying to find the Lagrange multipliers. And so the idea can basically then can we really kind of merge the bit? And so we try here with the idea, we propose the idea of tolerant barrier states, where we basically try to as I say, to kind of merge those capabilities of barrier states as well as augmented Lagrangian. Basically, the idea is to construct a barrier function. Basically, that's a summation of some sigmoid function and a soft plus function that allows us kind of to control the behavior of the barrier in the safe region as well as in the safe region. For example, as you can see in the top figure here, I'm showing here the classic. Yeah.
Can we stop the camera so that we can make a better use of the bandwidth?
Yeah, sure.
Can you guys hear us well right now?
Right now, yes, but the voice has been breaking all the time for me.
Okay.
Okay. So yeah, and as you can see in the top figure, for example, in green is shown the this tolerant barrier, and so we can control really how much we can approximate the classical barrier in the safe region, but we also can also kind of control the behavior of the barrier in the unsafe region. And as you can see here, B subscript X is the gradient with respect to the states, for example, and we can also control or tune the kind of by tuning this.
Yeah, I'm breaking the voice.
Breaking or?
Is it still breaking? Can you guys hear us?
Yes, now.
Okay. We allow for temporary constraint violation, and while trying to so that there's a way to approximate the barrier state solution when it's feasible, and also a huge advantage here is that we have information within the unsafe set, basically how much kind of the gradient of that barrier pushes us outside the unsafe region. As you can see in the top, in the bottom figures here, and the left we have the inverse barrier. not only around kind of the obstacle or the unsafe region, we have those gradients that are pointing outwards, but also inside. And we can control how much, kind of how aggressive those gradients or you know, yeah. Kind of the classical barrier and the tolerant barrier in this context here is that, for example, let's assume that we have this scenario where we try to hit the red X and the system starts at the green dot or circle. And so we can see that by nature as a local method, DDP starts by kind of the first iteration just points towards somewhere around the solution to reach the target. For the inverse or classical barrier, then it points somewhere around the target, but because it's kind of the target is surrounded really by the constraint, it couldn't find a way to go around and find the target, especially that there is no kind of utilization of the gradients within the unsafe region. On the other hand, for the tolerant barrier, we see the improvement. It could kind of find a way to iteratively get it closer to the target and eventually achieving a safe solution. And so, for example, here we also implemented this on a multi-agent scenario where we have two teams of two robots trying to switch positions while staying connected. They all start unconnected, so we're already in kind of the unsafe or infeasible region. So classical barrier cannot be used here. And so as you can see, they start by going towards each other. Those circles represent kind of connectivity of each agent. So they started by approaching each other, getting connected, and then switching positions while avoiding collision with each other and the obstacles and squares here. And of course, now going back, how is this compared to barrier states and AL? And so we compared them in multiple scenarios. For example, Dubin's car and a cluttered environment with those kind of unusual shapes of obstacles. And we can see here that in the left bottom figure, we have the safety and success rates. Basically, we can see that the barrier state, the classical ones, achieve high safety rates, but not success rates. On the other hand, tolerant and AL basically methods are able to. Now, comparing this with in a quadrotor, kind of a more complicated system with moving obstacles. So AL really struggles in general with moving obstacles. And so we can see here that tolerant barrier states was able to really kind of overcome the shortcomings of AL DDP when dealing with moving obstacles. So it was able to achieve a higher success rates and higher safety rate. And of course, another and a final kind of consideration here was the computation time. So classical barrier is not only easy to tune, it's really fast also to converge. It doesn't need much iterations, unlike AL methods. Now, tolerant barrier has also kind of the same behavior. It converges a lot faster than augmented Lagrangian methods. However, it does take kind of for each iteration more time to compute the solution, and that has to do, of course, with computing the gradients for the XR state and among other things. And that's all. Thank you. Those are just some references of the work.
Okay, thank you very much, Hassan. So this we have another 5-6 slides. So next, I'm going to go to kind of the work that we did on perception, and there's a motivating example here. We have working on integrating perception with control primarily for terrestrial vehicles, And right now we are also part of other projects where we see the limitations of existing autonomy stacks. So here's just a video that is kind of a motivation. It has to do with one of our previous work on integrating perception with model predictive control. The idea here is that you want to be able to go through this environment, and you have to be able to detect the gates, right? So you have essentially neural networks that you train to detect corners on the gates, all right? So when it comes down to safety and perception within a feedback loop, there is one level of asking the question of how can I guarantee safety when I have a camera within the loop, but there is one more fundamental question, which is how do I train the network so that it is robust to adversarial attacks, right? So here, what I'm going to show is that we're going to ask this question of how can I robustify the performance of a neural network when I train this neural network, and how can I make it robust against adversaries. And so typically, a lot of people in the area of autonomy think about, I will consider as customers of deep learning or customers of machine learning, in the sense that they will take tools from the ML and deep learning area and kind of use them inside autonomy for representation purposes, right? You want to be able to represent dynamics or cost functions, and then you use ML methods to do that. So here, what we're going to do is we're going to go in the opposite direction. We're going to use optimal control as a framework to kind of derive training algorithms for neural networks with a purpose to actually robustify their performance against adversarial attacks. And so the way to do that is by actually making a connection between the neural network as an architecture and a standard finite horizon optimal control problem. So the mapping between training and optimal control is as follows. You can think of the output activation functions for every layer of the neural network as a state. You can think of the weights of the neural network as control parameters. And then when you go from one layer to another layer, that is a one-step propagation of your dynamics. Layers, or the depth as the time horizon. Cost function that you're using to do use control cost because we are dealing with physical systems that have energy requirements, and we want energy requirements for the purposes of training a deep neural network less than a regularization cost. You kind of do this mapping, then you can ask the question. Done to show that backpropagation is nothing else than a version of the iterative Podriakin maximum principle. Okay, so backpropagating essentially is the backpropagation of the cause state that we have in the Podriakin maximum principle. And so what we have done here is to go one step further and say, okay, in optimal control theory, we know how to kind of ask the question of robust optimal control, right? And then the way to do that is by having minimax optimization problems. Now, this is robustness in the time domain aspect, where we have a finite time horizon optimal control problem, and then we have a optimal control U and the adversary V. And now we try to solve this problem. We have both control and the adversary being part of the dynamics, okay? So then we are going to use this formulation, right, to derive backpropagation equations that will backpropagate the value function within the neural network in a way that we are going to train the neural network in a robust fashion, meaning that we will we will optimize the neural network such that it takes into account adversary controller, okay, which in that case could be noise in the data, or it can be certain variations that you may have in the input of the neural network. And so, basically, what happens now is that one of the issues, I guess, the price that you have to pay is that now for every, you don't have only weights, you have also the adversarial weights that you have to use in order to be able to do the optimization, right? Because remember, we have mapped the weights down to controls, and therefore now we have the good controller and the adversary controller, right? And so what these plots just show is that they show that for every connection from one layer to another layer, you will have essentially two weights, one for the optimal control and one for the adversary control. And so this is how the algorithm works. Essentially, you will derive the backward pass, which is a generalization of the Riccati equation right now. Essentially, you will have a new formulation of backprop algorithm, which takes into account second-order dynamics, the second-order information, and you just follow the iterative process of training the neural network in this way. So this is a paper that we just have submitted for. To kind of keep the performance of the neural network in the classification tasks. Attacks, and we kind of outperform other previous methods in this area. This is a research direction that we want to be able to push forward and kind of see it in more in deeper neural networks and other types of neural networks. I just want to mention on millions of parameters. So scaling optimal control, scaling important. In the paper, you can see of how we can use the architecture of the neural network to impose Kronecker factorization on our value function so that we are able to scale the computation to millions of. From an optimal control perspective, that's a very large. These slides give you another form of another part of the really valuing looking into this research direction of taking optimal control methods and robust optimal control to kind of train neural networks against adversarial attacks. So what is next, right? So what we have now is we have an architecture. We kind of familiarize ourselves with this concept of differentiable optimization, and I think we took it one step further by showing that there's a theory that can kind of accommodate a lot of the previous work in the area of differentiable optimization. We are also inspired by a lot of problems that we see in our projects and in our ability to push algorithms into industry, right? When people work in industry, they don't really want to babysit their algorithms. They would like to be able to have ways to kind of tune these algorithms on the fly, right? Tuning is really hard. And when we publish academic papers, we always pick the best parameters for our algorithms. So I think the value of differentiable optimization is very important here. So this is the architecture that we have, right, where we have the nominal NPC and the auxiliary NPC, and with differentiable optimization, we can kind of learn different parameters either at the nominal level or at the auxiliary level. But now, really, we would like to bring perception into this feedback loop. And one of the questions that, some of the questions that we have to deal with is, okay, how do we bring perception, right? Like, do we, what is the state here, right? We typically think about the state as a state that has to do with mechanical properties of the system. If we keep this, if we still make this choice, then we have to kind of push the perception into the representation of cost functions, right? Where we have cost maps, and then we have to deal with 3D cost maps. And this is something that we see in the DARPA Racer project, for example, right? Now, if we kind of want to talk about perceptual states, then we have to find representations of features on images and find ways to propagate these perceptual states. So then one of the questions there would be are both the nominal and the auxiliary dynamics, do they have to be in the same state space? Do they have to share the same state? So all of these are actually questions that we would like to be able to address within the concept of differentiable optimization, which will allow us to automatically tune these different modules. And so, of course, we have done some work here on UAM vehicles, and we have had a very nice paper on parametric differentiable dynamic programming. And so we really want to kind of now go one step further and see how we can use, how we can work more with dynamics of these vehicles and with more like complex, complex simulation environments, and kind of use these dynamics inside the differentiable robust NPC framework. And so that's really the last slide, and this is all that we wanted to share with you today, and we're really open to any questions that you guys have and any feedback. Thank you.
Thank you, guys. But so half of your voice was broken. The audio connection was really not robust. But let's see if we have questions, and we'll post the recorded movie and slides on the website. Questions from the audience.
Hi, good morning. This is Kevin. Can you hear me okay?
Yeah,
Yes,
you are
Kevin.
great.
Hey, very nice presentation. Thank you. There was a little bit of audio challenge, but I think it was tolerable. I was just wondering, in the way these algorithms are implemented, is there memory so that when you've transitioned from one phase of the trajectory, you've had some disturbances that influence the solution, then is there memory for the next time when you get something similar to that?
Are you referring?
Let me give you an example. Okay, so you got an autonomous car, and you're on a wet road, and then all of a sudden now you're on a dry road. Now you're back onto a wet road. Is there memory from previously? Yeah.
So so far in what we have in this presentation for the project around ULI, we don't have this architecture, but there are other projects that we have worked and we are still working, in which you're trying to kind of identify what's the environment within which you are operating. And so your question is really an important question, because it kind of asks what are the mechanisms for generalization, right? Because you kind of tune your algorithm for an environment, and then you want to be able to see how you can generalize to a different environment. And then memory is one of these mechanisms, right? Memory will be one of these mechanisms. So from what I have seen, Kevin, so far, I think that architectures that will work here is something that has memory, but it has also its ability to fine tune while is operating within that environment.
Very good, thank you. I have another question too, if you don't mind.
Please, go ahead. Yes, go ahead.
Sometimes it's difficult for us to describe constraints as a function of the states. So, and as an example would be, say you're trying to, say you have a load limit in the structure of your vehicle. It's difficult sometimes to represent that as a function of a state of the system. So we have to iterate in industry between trajectory generators, and then they take those over into the FEM codes to estimate loads. And we iterate control design. So I was just wondering how much have you thought about these constraints in the MPC? Does that question make sense to you?
Yeah. So see if that are complicated in some ways, that are not, it's hard to.
Evangelos, you break up. Just talk at the microphone, or I don't know.
Okay, talk it through your.
Now you're muted even.
Okay, can you hear me now?
Good.
You are again muted.
I'm not muted. Okay.
Or is your speaker off?
No.
Are you answering the question? If you're answering, you're muted. We can't hear you.
Can you hear me now?
Yes.
Okay. So, if I understand correctly, the question is, there are constraints that are very hard to write down mathematically, right? But you can kind of generate trajectories, play them on the hardware in multiple iterations, collect data, right? And so how all of that it can be embedded within MPC? Is this the right way to?
Yes, that's good. So, like when we talk about,
is this really the question that you're asking me?
yes. So when we think about, loads in an aircraft, it's very difficult in our GNC simulations for us to model that. Okay, so we have a very difficult time modeling as a function of the state. That's really the challenge that we have. I was just wondering, have you addressed such a thing in your research so far? Over.
So far, no. So
one thing we did recently, I think if my understanding of the question is correct, one thing recently we did is to assume that we have some data to kind of measure those unsafe regions. For example, if it's an obstacle, then you assume that we have some LiDAR data or something to know the distance from the obstacle. And then we use Gaussian processes to kind of model those constraints, and then of course do probabilistic safety guarantees over that. If that answers the question, but yeah, we use what we did is we used some kind of machine learning methods to model or represent those constraints.
Very good. Thank you. That's all I had. Thank you.
Any other questions? Okay. Okay. So if there are no other questions, thank you very much. And I think I will see most of you in the review. Naira? We cannot hear you. I think you're muted. Can you guys hear us?